Greetings, physics enthusiasts. Welcome to our final video on momentum. So, momentum is Unit 5. This is AP Physics 1, Unit 5, Lesson 6, Lesson Final, and Lesson 6. A little bit. Not so much more on momentum, though, because this is the review. So remember, at the beginning of this chapter of this unit, we started with the impulse momentum theorem. The impulse momentum theorem. And I derived for you this equation. The net force on an object times the time that net force acts is equal to the object's mass times its final velocity minus the object's mass times its initial velocity. Force times time equals mv final minus mv initial. And we decided to name this product impulse, and we decided to name this product or this product, whichever one you want to talk about, momentum. There was a time when I circled this and I said, that's momentum. And people misunderstood and they said, so the mass times the initial velocity is momentum. What do we call the mass times the final velocity? And we call mass times velocity momentum. And therefore this is the final momentum and this is the initial momentum. So a shorter way of writing this, now that we have these names, is impulse equals change in momentum. Let's just be really clear and remember that the unit, since impulse is force times time, the unit for impulse is the unit for force times the unit for time. So the unit for impulse is the unit for force times the unit for time, newtons times seconds. Since momentum is mv, the unit for momentum is the unit for mass, kilograms, times the unit for velocity, meters per second. So the unit for impulse is newtons times seconds. The unit for momentum is kilograms times meters per second. But since I've got an equation here, the unit on the left should be the same as the unit on the right. These don't look the same. But if we remember what a newton is and multiply that by second, we should end up with this. Do you remember what a newton is? A newton is the unit for force. Since force is mass times acceleration, the unit for force should be the unit for mass times the unit for acceleration, meters over seconds squared. And this s cancels one of these s's, and we get kilograms times meters per second. So these units, newtons times seconds and kilograms times meters per second, are equivalent, same thing. All right, so that is our impulse momentum theorem. How is that useful? What is its utility? How hard I push something times how long, how much time I push that something. If I know both of those, and I know the mass and the initial velocity of the object, I can solve for and predict the final velocity of the object. So that is the impulse momentum theorem. Now, that led us to the law, meaning it's important, the law of conservation of momentum. Or shorter, we can just say cons of P. But this is the nice long way of saying it. The law of conservation of momentum says momentum is conserved. So the momentum before should be equal to the momentum after. Now, here's an example where it seems obvious that momentum is not being conserved, which must be incorrect because this law says momentum is conserved. So here's a coffee cup, and I could push it, and it'll slow down and stop. Well, it had momentum at the beginning, and then it didn't have momentum at the end. So was the momentum of the coffee cup conserved? No, the coffee cup, the coffee cup's moving, the coffee cup's not moving. So the coffee cup's momentum might not be conserved, but that momentum went somewhere else. So if there is a thing and its momentum changes, it's because that momentum went somewhere else. The money I have in my wallet, when I spend it, my money wasn't conserved, but the money itself was. The $50 I spent on that really cool thing, the money still existed. It just now exists in the store owner's wallet instead of in my wallet. So the law of conservation of momentum says that the total momentum before equals the total momentum after. So I could have, two objects, and they might have velocities before m1, v1, m2, v2, and they might interact or collide. And then this object still has mass m1, but maybe after it catches up to this one, it's going to be going slower afterwards. And maybe this one after the collision is going faster afterwards. This is still m2, but this would be v1 final, v2 final. These were the initial velocities. So that gives us our equation m1 v1 initial, this guy's momentum before, plus m2 v2 initial. And that total momentum before equals this total momentum after, m1 v1 final plus m2 v2 final. That's the law of conservation of momentum. So this is before, and this is after. Make sense? Now, energy is also conserved. I'm just going to say that, energy, Gy, is conserved. So, I throw the pen up in the air and it goes higher, 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 higher. It was moving at the beginning, so it had kinetic energy. At the end, it's not moving. Where did the kinetic energy go? Well, it became potential energy. And we studied energy previously. And we learned about this conservation of energy. And energy can change from one kind to another. Sometimes we just want to focus on the kinetic energy. So in these collisions among particles, this one could be going to the right slowly, or it could be going to the left, and we could collide head on. Sometimes in these collisions, kinetic energy is conserved. Sometimes. Sometimes Ke is conserved. And sometimes, other times, Ke, that says is, sometimes Ke is not conserved. Now, that doesn't mean energy is not conserved. It just means the kinetic energy is turned into other kinds of energy. The kinetic energy could be turned into gravitational potential energy. The kinetic energy could be turned into spring potential energy. The kinetic energy could be turned into heat. It could be turned into sound. There's all kinds of things that the kinetic energy could be turned into that are still energy. But sometimes the kinetic energy is not turned into other kinds of energy, and the kinetic energy itself is conserved. If the kinetic energy is conserved, we have an adjective for that. That's called elastic. If the kinetic energy is not conserved, we have an adjective for that, inelastic. No big deal, we just have an adjective that describes that situation. Now, the problem with these adjectives is that you've heard the word elastic before. And you think of rubber bands and bouncing balls when you hear the word elastic. That's not what this is referring to. This just means, it's just some adjective that you don't make any association with that means kinetic energy is conserved. And this is an adjective, don't make any associations, that means kinetic energy is not conserved. If kinetic energy is conserved, then I can say 1/2 mv squared of the first object plus 1/2 mv squared of the second object. 1 initial, 2 initial. That sum is the total kinetic energy before. And that will equal the total kinetic energy after the first object and its mass and velocity final, 1/2 m1v1 final squared plus 1/2 m2v2 final squared. And this equation is true because that's a collision where kinetic energy is conserved. Inelastic, I'm going to write the same equation with one little difference. So far, it's exactly the same. It's still exactly the same. The only thing I'm going to change, this equation and this equation are still the same. I'm going to take this equal sign and I'm going to make it not equal. Some of the kinetic energy went away. Instead of unequal, I could even write greater than instead, because this kinetic energy before the collision should be greater than this kinetic energy after. Some of the kinetic energy gets turned into something else. That's all it means. Now, if the two objects collide and they have separate velocities afterwards, if that's all I know, I don't know the answer. Is it elastic or is it the collision inelastic? I don't know. There are collisions where the two objects hit and they go off at separate velocities where kinetic energy is conserved. There are collisions where they collide and go off in separate directions and kinetic energy is not conserved. The word elastic does not mean, oh, they have different velocities. So this could look either, could be either of these situations. If they collide and stick together, so there's only one final velocity, that for sure I know is an inelastic collision. And since I know that for sure, they've come up with this third descriptor, not elastic, not inelastic, but they call it perfectly inelastic. If the collision is perfectly inelastic, it means the objects stick together. There's only one final velocity, and that's super easy, because then in my momentum equation, m1v, let's go back and do that over here. On the momentum equation, since v1 final and v2 final are the same, I can say m1 v1 initial plus m2 v2 initial equals m1, and I can just say v final plus m2, and I can just say v final. I don't have to say v1 final and v2 final because v1 final and v2 final are the same number. And therefore, I can write m1 v1 initial plus m2 v2 initial. Nothing changed. I'm going to factor out this v final, m1 plus m2 v final. This is a much easier equation to deal with because there's only one final velocity to find. Is this collision elastic or inelastic? It's inelastic. Specifically, even more information, it's called perfectly inelastic. They stuck together. For the collisions where they don't stick together, I have 1, 2 final velocities. If you're told the collision is inelastic, this equation isn't going to help you because this number doesn't equal this number. So you just have this one to deal with. If they tell you the collision is elastic, then in addition to this equation, you also have this equation. So you have these two equations that you get to use. And yay, you get to use the two equations, this one and this one. But there's a bit of algebra. And there is very likely on the tests you take, tests, final exams, AP exams, there's likely to be a situation where you have to plug the numbers in here, plug the same numbers in here, and solve those two equations for two unknowns. And I've shown you how to do that. And I promise you, every single problem, you follow the same steps in the same order. So follow those steps in that same order. And I think that is the majority of the stuff in this chapter. I know it was kind of a short video, but that's really all I have to say. I'm going to check my notes. Yes, that's all I have to say. So until next time, have a great day.